Right, here we go with part 2 of lesson 1.2. We're going to be taking a look at just some different types of functions and some symmetry, things like that. So I am going to reference a few pages out of your textbook, so you're always welcome to make note of those or open that up and you can kind of follow along. As far as symmetry goes, when we're looking at functions, let me kind of explain these, and I'm going to show you some great diagrams that are in your book that are going to help give you some clarity on those. But when you look at a few different types of symmetry, a graph can be symmetric to the y-axis, it can be symmetric to the x-axis, or it can be symmetric to the origin. If it is symmetric to the origin, that would be an odd function. Symmetric to the origin simply means that if you are looking at a graph, if you rotate that graph 180 degrees, you would be looking at the exact same graph that you started with. And I'll show you an example of that here in a minute. An even function is one that is symmetric to the y-axis. That means that the y-axis acts as like your mirror. If you were to fold your graph in half right along the y-axis, the left side would lay on top of the right side. And so that would be your even function. If it doesn't fit either one of those descriptions, then we just say it's neither one of those. A graph that is symmetric to the x-axis still has symmetry to it, but it doesn't fit the odd or even description. So let me take you to some diagrams. Here's the pages we're going to be looking at. So let me open that up for you. So let me start on page 88. And here is an example of an even function. So this is one that is symmetric to the y-axis. So here's my y-axis. This is my mirror. If I were to fold this graph along this line, you can see that the left side would lay right on top of the right side, and therefore it's an even function. So that's sort of the idea for how to look at an even function graphically, but we're also not always going to be looking at a graph. We need to know how to do this algebraically. And so the idea is, if I were to have a function laid out in terms of y and x like this one is, it would be even if I can replace all of my x's with negative x and come out with the exact same function, right? And we'll take a look at that. So just think of a real basic one like this one. This is y equals x squared. If you replace that x with negative x, do you get this exact same function, right? And we know that we do, because negative x squared becomes positive x squared, right? Because you square a negative and it becomes positive again. So that's why this one becomes an even function. Let me go to the next page and show you our other two types of symmetry. So if it is symmetric to the x-axis like this one is, so you can see I can fold this graph along the x-axis, this half would lay on top of this half. So it does have symmetry, but it is not odd or even. This is not actually even a function because it would fail the vertical line test, as you can see. There's a rule to it, right? So all that's happening, if you take any point and change the sign of the y-coordinate, you would get the mirror image on the other side of the x-axis. So there is a rule to this, and it does have symmetry, but it is not considered an odd or even function. So here's the third type of symmetry, which is one that is symmetric to the origin. Symmetric to the origin is an odd function, right? It's just another term for it. So, and again, that means if I were to take this graph and rotate my page 180 degrees, I would be looking at the exact same graph that I am now, right? And so the algebraic rule for that is, if I can replace x with negative x and all of my signs change for every term in the function, then I have an odd function. And we'll see some examples of that here in just a second. So let me go back to our examples so we can do some together. So let me go back to our notes. Let me turn the page. So here's some we can do together. So just take a look at this first one here. So we're going to try to figure out if they are odd, even, or neither. Let me try to refocus really quick and see if I can make it a little more clear. So if you take a look at the first one here, if I were to take that x and replace it with negative x, what would happen to my function overall? Would my signs overall change? Would they overall stay the same, or neither one of those? Would it be some mixture of change in signs? So if you look at this one, so if I replace that x with negative x, well, I would still get 2x squared plus 1. And so that's what you're seeing right here in this explanation. So we're replacing x with negative x, but negative x squared is still x squared, right? And so I get the exact same function, 2x squared plus 1, that I started with, which makes it an even function, right? And so that's what this is saying right here. Much easier always to look at the graph, really. I can see that this folds across the y-axis, but we're not always looking at a graph. So it's kind of good to know both ways of doing it based on the graph and the algebra behind it. And we're going to have you try some of these on your own in a second. I'm just going to talk you through a couple examples. Let's do the same thing with this one. Replace both of those x's with negative x, and what happens? So here's that one going on right down here. So my leading term right here is now negative x squared, and then my negative 2x, and we're changing the sign on that one as well. This one doesn't have an x, so it's just going to keep the plus 3. So if we do a little cleanup on that, here's the function that we now have, right? And so here was the original function. Let's compare that to the one that we have now. So you can see that this one stayed the same, this one changed signs, and this one stayed the same. So in other words, there wasn't an all or nothing scenario, right? They either have to all stay the same or they have to all change in order to be odd or even. And since there's a mixture of some that stayed the same and some that changed, we'd have to say it's neither odd or even, right? So one more here, I'm going to take example C. So again, I'm going to replace my x's with negative x, and let's take a look and see what happens. So here you go. So replacing the x's with negative x, we're going to do a little cleanup on that, and this is what you get. And then again, we need to compare this to what the original one says. Well, the numerator changed signs. The original was positive x to the third. Now it's negative x to the third. The bottom one, the bottom sign stayed the same. It was positive x squared. Now it's still positive x squared. And then the minus 1 is still minus 1. So this one is really tricky. So that's why I really wanted you to see this one, because this one is a fraction. When the numerator changes signs, right? You guys know, you've seen fractions written in a few different ways, but when you have a negative up here, that is the same thing as putting the negative in front. So that could now be written this way and mean the same thing, right? And so what we're seeing on this is, and this is what's kind of unclear when you write it this way, because it looks like there's a mixture of changes here. It looks like this one changed, but this one stayed the same, so maybe it's neither. But when you consider whether it's overall positive or overall negative, because just the numerator changed signs, and if we were to write it this way, what we're seeing is there's an overall sign change of a negative here. So this one's kind of tricky. It's much easier when it's laid out without a fraction. So that's why I wanted you to see this. But so we are seeing an overall change in sign according to that, which is why this guy is an odd function, even though that one's a little tricky. So we're going to give you two of these guys if you want to give these a shot real quick before I do them ahead of you. You can pause right here and give them a try. So on this first one, if you replace x with negative x, do you come out with the exact same thing that we started with? And you can see that we do, because it's an even exponent, still 3x squared plus 2, so we get back exactly what we started with, therefore it's an even function. You may start to notice some shortcuts on here. Let me just point one out, in case you didn't catch it already. An even function is only going to exist when your x's contain even powers, right? So if I have all even exponents, right, then I can come out with an even function because of what just happened right here. Your negatives will still be positive, right? So that's only going to happen when you have even exponents. An odd function is only going to occur when you can get that overall sign change. So when you're looking at even powers, this is not going to change signs, right? Because it's even. And so that's where you're not going to see that odd function in cases like that. So if you look at one like this, right off the bat, we may already notice, sorry if it's a little fuzzy, this says x squared minus 2x. We may already notice that I already know this is going to be neither, because this one is going to stay the same because it's an even power. This one is going to change because it's an odd power. So because one stays the same and one changes, I'm not getting an overall shift in sign. Therefore, it's going to be neither function. Right? So we might start noticing some shortcuts like that. All right, let me move on here for you. So some of these things are a little out of order because I had to sort of create them and fit them in where I needed you to see certain things. So we're going to start with this, and we're going to kind of finish off the lesson here by going into some vertical and horizontal asymptotes. So vertical asymptotes are going to look like this, right? This is an imaginary boundary line, so it wouldn't really show up on the graph, right? They drew that in so you could see it, but this is an imaginary boundary line that your graph did not cross over. It approaches it but does not touch it. Your horizontal boundary lines or horizontal asymptotes would run something like this, and again it becomes this like imaginary line that your graph sort of hugs up next to or approaches as we see that. So let me show you something at the top of page 91. So here's a better picture, better diagram, so you can see the vertical red dotted imaginary lines are your vertical asymptotes, and your horizontal asymptote looks something like this. So a couple properties that you can kind of see on this. Whenever you see this is a notation we're going to get used to. We're going to do a whole chapter in calculus on limits to start things off when we do that down the road. But what they're saying is the limit of your function as x approaches negative infinity. When you see x approaches negative infinity, that just means as your graph goes to the left, right? So here I am as x approaches negative infinity. And if you see it written this way, this is just your graph as it goes to the right. So as x approaches positive infinity, would look something like that. Your horizontal asymptotes are always written as y equals a number because it's just a horizontal line. And your vertical asymptotes are always written as x equals a number since they're vertical lines. When you look down here at the vertical asymptotes, now you're seeing what is the limit or what is the value that your function is approaching as x approaches a from the left. That little minus sign means you're approaching a number from the left. The little plus sign means you're approaching a number from the right. So what this is telling you is as my graph approaches a from the left, so this is my a value here, whatever this is, -2 it looks like. So if this is my a value, or this can be an a value, this is a b value, this is a y value. But as I approach a from the left, you can see that my graph is approaching negative infinity. As I approach that same a value from the right side of it, my graph is approaching positive infinity, right? And so that's what this is saying, is as I approach a from the left, my function is approaching positive and negative infinity, or negative infinity, sorry. So again, as I approach it from the right, I can approach either positive or negative infinity. So here's my a value at +2. As I approach it from the left, that's what this is saying, my graph, my function is approaching positive infinity. As I approach that same a value from the right, my function is approaching negative infinity. Right? And so that's what this notation is telling you. Something I want you to get used to because we're going to deal a lot with limits as time goes on here. So I just want you to start interpreting what all those symbols are trying to tell you. So let me go back to our example page here. So how do we identify them or how do we find them? Two simple rules you can follow here. To find a vertical asymptote, you simply set your denominator equal to 0 and solve for x. Your horizontal asymptote is you set the entire function equal to 0, right? And so let's take a look at a couple of these guys here real quick. And I'll give you a couple to try on your own down here at the bottom. So identifying these guys, these asymptotes. So for the vertical, we're going to set this denominator equal to 0, and we're going to solve for x. So if you were to take x squared minus 4x plus 3 and set that equal to 0, which you would solve by factoring. So if I set this equal to 0 and solve for x, you can see that I'm going to get +1 and +3 as my vertical asymptotes. We always write these as an equation, so you would never write it as my vertical asymptote is 1 and 3. a vertical asymptote is always written as a vertical line. So you got to write it as an equation. So these would be the two equations of our two vertical lines. For the horizontal asymptotes, they're a little more, little not as straightforward. So let's just take a look and tell you what this is going on here. So again, as I said, if I set the overall function equal to 0, like what are we looking at? We're setting y equal to 0. So what this is trying to tell us is the limit as x approaches infinity. In other words, what this is telling you is what value is your graph approaching as your graph goes to the right. Right? So if I look at my graph, as my graph goes on forever to the right, what is it approaching? And you can see that it is approaching 0. Right? So right here, I do have a horizontal asymptote of 0. And so much easier to figure that out as you look at a graph. But that's how we would interpret this, is what is my graph doing or what value is it approaching as my graph moves to the right, as x approaches infinity, in other words. Right? And so because it's approaching 0, we do get our horizontal asymptote of y equals 0. Horizontal asymptote is always written as y equals a number. We are going to learn some rules to horizontal asymptotes that I think will help you. So in this case, one of those rules that you would have learned is when your highest exponent on top is smaller than your highest exponent on bottom, your horizontal asymptote is automatically going to be y equals 0. So that's just one of the rules we're going to see. That will make life a little easier when it comes to horizontal asymptotes. For this one, just a note, my horizontal asymptote, you'll notice that my graph is approaching 0 forever to the right. It's still doing that on the left, but something kind of interesting takes place on these. In a horizontal asymptote, you can have your graph cross a horizontal asymptote. As you'll notice, this one right here crosses at this point, crosses the horizontal asymptote, but then it comes back up to it, and now it's forever approaching 0 as x approaches negative infinity, or as my graph goes to the left. Right? So you'll never cross a vertical asymptote, but your graph can potentially cross a horizontal asymptote. Right? It's still, after it crossed, it's still now coming back up towards it, and it's still approaching 0 as we move further to the left. So if you want to try a couple of those, good time to pause this. I'll go through a couple of these guys here real quick so you can check if you're trying these on your own. So for the vertical asymptotes, if I set x minus 5 equals to 0, so if we do that, obviously if we solve, I get the equation x equals 5. So there's my vertical asymptote. Always good to check these on a graphing calculator too. If you ever want to graph these in your graphing calculator, or if you're using Desmos or something like that, you can take a look and see what it looks like. Easy to spot those vertical asymptotes when you do that too. For my horizontal, again, I just set y equals 0 in a case like that, and there's my horizontal. As I mentioned earlier, my top exponent is technically smaller than my bottom exponent, if you think of this as x to the 0, since there's no x up there. So if my top exponent is smaller than the bottom, I know y equals 0 is my horizontal asymptote. If you were to take a look at the graph for this one, I'll give you a quick sketch here. But this is just a rational function that has been shifted right 5 units. So you're going to get something like this if we were to graph it. So I got my vertical right here at x equals 5, and you would see the horizontal right here at y equals 0 would be our two asymptotes. Sorry, I drew that curve a little wrong. It would do something like this. So what we would say is, as x approaches infinity, in other words, as I move to the right, my function approaches 0. Right? It's approaching that 0 boundary line right there. So that's where we get our horizontal asymptote. Let me give you a couple more over here. So for this guy, if I set x squared plus 1 equal to 0 and solve it for my vertical asymptotes, you'll notice on this one I cannot square root a negative. So there is no horizontal asymptote, or sorry, there's no vertical asymptote for that guy. This one should still, I'm still going to get y equals 0 as my horizontal. since my numerator exponent is smaller than my bottom exponent, right, I know that I'm still going to get y equals 0 as my horizontal asymptote. All right, so if you look at this guy here, again, as far as my vertical asymptotes are concerned, I'm going to set x squared minus 3x minus 4 equals 0 and solve it. Just a basic quadratic, you can solve that guy by factoring, but if you solve it, you're going to see that your vertical asymptotes on that one are going to be x equals -1 and x equals 4. As far as the horizontal asymptote, again, it's going to be at y equals 0. However, if you remember your transformation rules from Algebra 2, you can see that this graph has been shifted up 2 units. So that's everything. That includes your horizontal asymptote. So typically your horizontal asymptote would be at y equals 0. But according to this, it's been shifted up 2 units. So now it's at y equals 2, right? And so now my horizontal asymptote is going to be up here at y equals 2. So these guys you can always check, at least for now. Not a bad idea to check these on a graphing calculator or on Desmos, and you can see that shift taking place to help you see those horizontal asymptotes. Let me take you to one last idea to close out section 2 here. So let me take you guys through these last couple examples here. There's a couple tricks involved that they kind of threw in as a little bit of a curveball here. So I wanted you guys to see how to approach these. So the best way to match these up with certain graphs to see where your asymptotes are. Notice on these they're not technically asking you to find the horizontal asymptotes, but they want you to recognize what's taking place here within these given scenarios. So what we're going to do is we're just going to look at the 2 leading terms in order to help us figure out what our graph is approaching as we go to the right, as x approaches infinity. So we're going to match these. I'll show you the graphs here in a second, but I want you to note a couple things here. So what is this graph approaching? So as we talked about earlier, my top exponent is smaller than my bottom exponent. So we already know this one has a horizontal asymptote at y equals 0. So when I go to match these up with certain graphs on the next page, I should find the one that has a horizontal asymptote at y equals 0 should take care of this guy. You'll notice this is the only one that does that. These exponents are the same. This one has a top exponent that's bigger than the bottom exponent, and so does this one. So this is the only one that would have a horizontal asymptote at y equals 0. So if you look at the graphs on the next page, or on our book page, right, which one of these graphs has a horizontal asymptote at 0? So if you look right here, this is the only one that approaches 0 as x approaches infinity. So as I go to the right, you can see that the function is approaching 0. So I know this would match with that first example, for example A. But if you look at the other ones, so let's see if we can take that same approach. So I'm just going to look at my 2 leading terms, and I'm going to simplify them. So if I just looked at 3x squared over x squared, right, if I simplify this, x squared over x squared can cancel. And so I'm just looking at y equals 3 to see what my graph is approaching. So which one of the functions or the graphs on the next page is approaching y equals 3 as x approaches positive infinity? So if I go back to these functions, so as my graph goes on to the right, or sorry, as I move to the right, what is our graph approaching? And you can see right here that this one has a horizontal asymptote at y equals 3. So I know this graph would match the example we just looked at on the other page, right? So here's my horizontal asymptote as y equals 3. I can see that this is what the graph is approaching as x approaches infinity. And so I know this one, and this is the only one that does that, so I know this one would fit that description. So let's look at the last 2 here real quick. So on this one, in both of these cases, as I reduce, so if I take the leading term over this leading term, if I reduce this, I come out with just 3x. So that means that the graph of this should be approaching this line as I move to the right. Well, what does a line of 3x look like? All right, so here's just a basic, if I just said graph the line y equals 3x, how would you graph that? Right, it would be a function that starts at 0 and goes up 3 over 1. Right, so it's going to be a line that looks like this. So we need to find which of those graphs is approaching this line as I move to the right. So if you look at these, so if you look at this one right here, so you see how I could kind of draw that same dotted line of y equals 3x right there? And that's what this graph is approaching. So for this one, let me take you back so you can see it. So this graph, if I were to draw it in, is doing something like this. Sorry, it's a little ugly. But that's what this one is doing. So as it approaches the line of 3x, my graph is getting closer and closer and closer to that dotted line. So that's the one that we could match up with this guy right here. Let me show you one last case. Again, I'm going to start by just taking the leading terms and reducing. As you look at this one, as I reduce it, I'm just going to get 3x squared. Well, that's not linear, right? So my graph is not approaching a line. Asymptotes are always linear. So if this is a quadratic function, which it is, then there is no asymptote that this one is approaching. So for this one, as far as end behavior goes, this one is not approaching a line. It must be approaching infinity. All right, if it's not approaching a value, then it's got to be approaching infinity. So if you go back to our examples here, so if you look at this one right here, as I go to the right, what is my function doing? It's simply going up and up and up and up. It's approaching infinity. It's not approaching a specific value. So because of that, we know this last example would match up with this graph right here. So a little tricky on those. Don't panic too much if that didn't all sink in right away. We're going to get plenty of practice on limits and asymptotes and all that fun stuff. So, but that's going to be it for this one. Just wanted to help you out with a few examples that would relate to some of your homework questions as you look at those. Hopefully that helps, but I'm happy to help with those on as much as needed, but that's going to be it for 1.2.